I like to go through pages 7, well, parts of 5 through 8, especially ones that involve calculators. So let's just, I know you guys did this for homework, but I want to kind of go through each of the concepts and see if you guys have any questions. Okay, so page 6, we did the shadow problem above. Okay, so let me highlight some of these problems here. This is number 6 on page 6. Okay, it says the graph of a function is shown. Which of the following could be the graph of f prime? So this is the original graph, which means that if you want to create a sign line, the sign line will look exactly like what you expect from the graph. Relative max is that I'm just creating values for myself so that I can have some pinpoints. I call this -1, I call this +1. Relative max at this x value, relative min at this value. I know my graph is rising, falling, followed by rising. So positive, negative, positive. Concavity, I can kind of pinpoint my point of inflection to be at 0, concave down, followed by concave up. So I know how my sign line is going to look, but then I got to translate this onto a derivative graph. Well, I know that my x-intercepts must be at -1 and 1. I know that to the left of -1, I'm expecting a positive slope. Positive slope is going to have to live above the x-axis. So if it's above the x-axis, it's going to have to come down to this point, kind of like an anchor point here. Okay. Between -1 and 1, my slope is going to be negative. Negative means lives in the negative region. Doesn't mean that my graph is going to display negative slope, but it just show negative values. So it's going to be below, come back up again, and then to the right of 1, positive slope above the x-axis. Okay, we know there must be a point of inflection at 0. Point of inflection on the derivative graph looks like a relative min or relative max. So we see there's a relative min that corresponds to a point of inflection. Negative concave down on a derivative graph will display a negative slope. So we see that's the case. Negative slope means concave down. And then to the right of 0, concave up would be positive slope. Answer choice B. Okay, number 7, f prime is given. Which of the following is our graph decreasing? So decreasing is wherever my f prime is negative. So I'm going to go through my steps, though, for first derivative test. First, set f prime equal to 0. And then I find critical points, create sign line, and test my intervals. So set f prime equal to 0. It's easier to set this equal to 0. Now, I don't find the derivative because it's already setting at the derivative level. So I set f prime equal to 0, but it's easier to find critical points if I have common denominators. So I made this x cubed over x minus 2 over x. So my derivative rewritten is x cubed minus 2 over x. If I set the numerator equal to 0, I can find a critical point. If I set the denominator equal to 0, I also find critical points. Numerator gives me cube root of 2. Denominator gives me 0. But now I still got to go through and test my interval. So 0 and cube root of 2 goes on my sign line. I choose values in each subinterval to insert into my derivative to see if I get a positive or negative value. So if I plug in -1 into my derivative, I get a positive, which means positive slope. If I plug 1 into the derivative, I get a negative value, which means negative slope. If I plug in 2 into the derivative, I get a positive value, so positive slope. So now I know my graph, how my graph's going to look. It's going to rise, fall, and rise again. Okay, so decrease is going to be in this interval from 0 to cube root of 2. Okay, number 8, which of the following is true about 1? So it's asking you to compare the y value, the slope, and the concavity. So we know the y value, that's just 0. That's just a y x-intercept. Right? We know the slope at 1 is positive. We don't know the exact value, but we know it's positive, so we can kind of put that information down. And then we know the second derivative at 1, this is part of a concave down graph, right? So concave down graph means second derivative is negative. So if you're comparing 0, positive, and negative, you can still order them even though, or put them in increasing order, even though we don't know these two values, but we know one is negative and one is positive. So the negative must be the smallest value. 0 is going to be next, and the largest value must be the positive, which is our slope. Okay, page 9. G is differentiable. We know that g of x is always less than 0. Okay, and it says which of the following is true. Okay, so f prime, it's asking about relative max, relative min. So we're going to make ourselves go through the first derivative test. So first derivative test, we set f prime equal to 0, and we find critical points. So we set x squared minus 4 equal to 0. We get 2 and negative 2. All we need to know about g of x, g of x is a negative value. Okay, that's all we need to know. So I'm going to identify my critical points, place them onto my sign line, and choose values around my interval, insert into my derivative. So if I plug negative 3 in here, negative 3 minus 4, that's a positive, but I know g of x is negative. So positive times negative, or positive times negative is negative. Okay, I can insert 0. 0 minus 4 is negative. G of x is also negative. Negative times negative is positive. Insert 3 into x. Positive times negative is negative. So I know there must be a relative min at negative 2 because I know how my graph is going to rise and fall. A relative max at 2. B. Okay, number 10. Second derivative is given. Inflection points. Okay, we know inflection points comes from the second derivative, and we set the second derivative equal to 0. But this is where I want to make sure that that we make sure we go far enough into the problem. This is the easy mistake that I see students make is students understand that second derivative or inflection points comes from the second derivative. They know to set equal to 0. But then once they solve for x, I see a lot of students just go ahead and stop and say, okay, I have my x values, so those must be my points of inflection. But at this point, you haven't gone far enough. You found candidates for points of inflection, but you haven't confirmed that these are inflection points yet. In order to be a true inflection point, there must be a change in sign on either side of that critical point. So you have to create your sign line, identify your critical points, identify all your points in between, insert each of them into the second derivative function, and see if there's actually a change in sign. So in this case, it's concave up, concave down, concave up, concave up. 2 is not a point of inflection because there's no change in sign. So the change in sign is only going to be at negative 1 and 0. So here it's a little bit, I wouldn't say tricky, but it is testing students to see if they can distinguish the difference between just critical points and true points of inflection, right? So we haven't gone far enough if you just stop here. Okay, number 11, select the values of second derivative as given. Which of the following statements is true? So if you plot these points here, 0, 5, 1, 0, 2, negative 7, 3, 4, if this is part of a second derivative graph, you know your points of inflection is going to occur where it crosses the x-axis. So here's a potential point of inflection, right? 1, 0. Because you're looking at this point saying, okay, I see a point that's a y value that's above 0, another y value that's below 0. So if I'm going from concave up to concave down, then this must be a point of inflection, right? Well, the tricky thing here is that, yes, the sign does change from positive to negative, but we can't guarantee that it's actually going to cross the x-axis at 0. It could do this. It could hit the x-axis, pop up to the positive region, and then reach the negative somewhere between 1 and 2. So we don't know exactly, we can't guarantee that our point of inflection is going to be at 1. So our answer choice is not going to be C. However, we do see a change in sign, and the graph is connected, so it must cross the x-axis somewhere between. And so that's the best we can say, that the graph is going to change concavity somewhere in this interval from 0 to 2. We see a change in sign, but it's not guaranteed to be at 1. It could be at the value slightly to the left or to the right. If it, it may not cross the x-axis like the graph I drew here. Okay, number 12, g of x. For what value of k does g have a critical point? So critical points comes from the derivative. We set the derivative equal to 0. To find the derivative, I have to go through product rule. So f prime g plus fg prime. Replace g prime with 0, and then just algebraically try to solve for x. Sorry, solve for k. A lot of things will cancel out, go away, merge the fractions together, and I get k equals -3. Okay, let's go to page 8. Now, page 8 is going to be true calculator active problems. So I want to kind of go through these problems with you. So these are probably what calculator questions will look like, especially if it's dealing with from a derivative first semester topic. Okay, it says let f be the function with the first derivative given as f prime. At what value of x does the graph attain maximum value? So if we think about a derivative graph, the maximum value is going to occur when my slope changes from positive to negative. So what that means is on a derivative graph, it's going to be the x-intercept where the graph crosses from a positive region to a negative region. Okay. Now, if you're using a graphing calculator, that's great. You can just graph this and then focus in on your 0 feature and get to that point. But if you're using a 36 Pro, you're going to have to look at your table of values and see where does my table of values actually change signs. Okay, once your y value changes signs from a positive to negative, then you can kind of pinpoint where that guesstimate where that x-intercept is. You can always decrease your step to be a smaller value like 0.01 or 0.02, and then keep looking at those y values to see where does it change signs from positive to negative. That's where your relative max is going to occur. Okay, number 14. The graph of e to the tangent x minus 2 crosses the x-axis at one point. What is the slope at this point? So here's my curve potentially. I want to find the slope at this point, but first I got to figure out where that point is. So I have to sketch the graph, find the x-intercept, which is 0.606, and now I want to find out what is the exact slope at 0.606. So I'm going to have to use my derivative feature and derivative feature. Math 8 on the graphing calculator, or you can do the d over dx. You can type in your function and then plug in the x value, ask the calculator to find the slope, the derivative at that point for you, and that will get you 2.961. Okay, 15. The derivative graph is given as f prime. On what interval is the graph increasing? So if you're looking at the derivative graph, your increasing is going to be where it sticks above the x-axis. So if it's above the x-axis, you're looking for this interval here. So first, you want to find all your x-intercepts, and then you want to look to see where it's above. Where it's above is going to be between 1 and 1.691. But if you're using a 36 Pro, you're going to have to just look at your table of values and see where it crossed the x-axis, where the positive values, y values are going to be before it dips down to below the x-axis. And that's going to be your interval for positive slope. Okay, 16, same idea. There's my derivative graph. I'm going to sketch my derivative graph. A relative max is not going to be your peaks and valleys. Your relative max is going to be your x-intercept, where there's a change from a positive to a negative slope. That's your relative max on the original graph. Okay, number 17, derivative graph is given. How many points of inflections? You know, a point of inflection on the derivative graph is going to look like the peaks and valleys of your derivative. So You sketch your derivative function in your calculator, and you just count your max and mins. I see 5 max and mins between -2 and 2, so there must be 5 points of inflection. Okay, it's a little bit harder on 36 Pro. You're going to have to look at all your Y values and see, okay, where's my Y values start to increase again? Okay, so there's a valley. Okay, increase, 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 and then my Y value is going to start dipping down. Once it starts dipping down, I see, okay, there's a peak. Oh, goes down, comes up. Okay, there's a valley. Goes up, comes down. That's another point of inflection. Negative, and it starts increasing again. So, right. So it's a lot of scrolling through your table of values if you're using 36 Pro. Okay, number 18. Velocity is given. What's the acceleration? You know, acceleration is just the derivative of velocity. So you can use your n-deriv feature and then ask the calculator to find the slope or derivative at 4. So do n-deriv v of t, and then plug in 4, and make the calculator find the slope for you. Math 8 n-deriv feature. Okay, so these are the most common types of calculator questions on the AP exam. Now, your calculator section is going to be a lot shorter than your non-calculator section. Calculator multiple choice is just 30 questions. On the calculator section is only 15 questions. But you're going to feel like you have way too much time on the calculator and not enough time on the non-calculator. I think they've kind of done adjustments to make it more balanced, but it still feels like, you know, you just have too much time on the calculator section. Something I want to point out to you with calculator section is that not every problem requires the calculator. So if you're trying to force the calculator onto every problem, sometimes there's no need for it. There's no use with the calculator. So just know that on the calculator section, you're free to use the calculator, but don't think that every problem requires it. Okay. So sometimes you may be just kind of figuring out, how do I do this problem with the calculator? A lot of times doesn't require the calculator. Right. You just have the option to use it if it calls for it, if there's a need for it. Okay. Moving on to second semester topics. Okay, so here are the second semester topics that will show up on the Thursday quiz. Riemann sums, first theorem, second theorem, average value theorem, integration rules, use substitution. We'll probably spend some time Monday and Tuesday doing that. Solving differential equations. Hopefully you guys feel more comfortable with it since we've seen quite a bit of it over the course of the FRQs. Area volume, disk, washer, cross section. Now, it's been a while since we've done this. This is the very last unit that we did, but I purposely avoided it during AP review because I felt like that was the most recent thing. So that was the thing you least needed to review. But now that we've done all the AP review and we still haven't gone back into area volume, let's go and spend some time today doing that. I don't want us to forget this. Most of you guys did really well in this section, so hopefully this will still be a strength for you on the AP exam. Okay, go to page 12. We're going to spend our class time today working through every problem on page 12, making sure you guys are still strong with these topics. Okay, before I do these problems, though, let me just do a quick review of disk and washer method and make sure that the formula still, you still remember the formulas here. Okay, so here's an example here. Let's say we had a graph y equals 4 minus x squared. Okay, and let's say this graph is only in the first quadrant. Okay, so something like this. All right, so let's say we have our graph, and let's say we are rotating around y equals 0. Okay. The first decision we have to make is, are we dealing with washer method or disk method? And we have to draw our dotted line. Our dotted line in this case is going to be right at the x-axis. Okay, so I'm doing some examples before we jump into the packet. Now, look at the axis in relation to your shaded region. Is this going to be this method or washer method? What do you guys think? You guys remember? This method, okay, because there's no gap, right? There's your dotted line is up against the flat surface, meaning that there's no gap, there's no hole, there's no need to subtract another radius out. So all we need is one radius. Okay, we always draw the radius perpendicular to your axis of revolution. So my axis is horizontal, so my radius is always going to be vertical, right? Okay. When you see a vertical radius, you know that you're dealing with algebraically a simpler setup, because typically you don't have to rewrite your equation. It's already given to you. So you just have to identify what the top of the radius is touching, what the bottom of the radius is touching, and then spend time to subtract them. Okay, so the top of the radius is sitting at the 4 minus x squared. The bottom of the radius is sitting at the 0. Okay, and now we just plug into our formula. This method only requires big radius squared. And now we just insert in. Our bounds is in terms of x. So from 0 to 2. Typically, if it's on AP exam, they'll just ask you to do the setup, or if they ask you for the answer, you can plug this in the calculator. Make sure you leave pi out of your calculator. You just enter that in, and then you just attach pi to whatever numeric answer you get. Okay, so that's one thing I want to review. Let's look at this scenario here. Same curve. But now, let's say we're rotating around a different line. Let's say we're rotating around x equals 2. All right, disk or washer method here? What do you guys think? Okay, rotating the shaded region around this axis. It's touching. Is it good enough for this to be this method? No, there's a gap here, right? It's not up against a flat surface. Not every part of the line is touched by the curve, so we got to do washer method. So washer method requires us to draw 2 radius. Always start on the dotted line. This is where I see some students make mistakes here. We never want to connect that distance between the shaded region. This is the center of your object. You got to include the center if you want to build a radius. So from the axis revolution, you're going to extend to the furthest boundary that you see. And then from the axis revolution, you'll extend to the closer boundary. And then you have big R and little r. Okay. Now, as soon as you see a horizontal radius, you have to make sure, just to prepare yourself, that there's some additional work ahead of you. Okay. These equations are not suitable for right minus left. So I got to rewrite them in terms of x. I got to solve as x equals. So if I rearrange the equation here, I get x squared equals 4 minus y. Get the square roots. And now this represents the curve. Okay, so let's build our 2 radius, big R. Right minus left, right endpoint is sitting at the 2. The left endpoint is sitting at the 0, so 2 minus 0. Okay, little radius. Right endpoint is sitting at the 2. Left endpoint is sitting at the curve, which is the root 4 minus y. Okay. And then we got to worry about our bounds. Our bounds is from the lowest to highest y value. Okay. And your washer method looks like this. Big R minus little r. squared. Make sure that you're squaring them separately, that you're not doing r, big R minus little r, and then doing one big exponent. The exponent has to come twice. Okay, so just a quick review with disk and washer method. And then let's look at page 12, where we can do a practice involving a cross-section. Okay, so I'll review the cross-section as we look at number 14. Okay, so here is page 12, number 14. Let R be the region in the first quadrant bounded by the graph of y equals x squared and y equals square root of x. Okay, so y equals x squared, we know that's the parabola in the first quadrant. Y equals square root of x, we know that's just the radical function that's going to be sloping down. So there's my shaded region. Okay, the base of a solid whose cross-section perpendicular to the x-axis are squares. So this is not going to be a rotation problem. All we're going to do is we're going to find the base, match it with one of the formulas, and then put into our volume formula. But first thing is we got to decide how to draw our base. It's always going to be vertical or horizontal. So which direction is this? It says perpendicular to the x-axis. Which direction is that? Is that vertical or is that horizontal? Vertical, right? So x-axis is here. Perpendicular means I got to form a 90-degree angle with it, so it's going to mean it's going to be vertical, right? So make sure you pay attention to the words here. You know, don't just assume that it's one or the other, right? But it'll give you very specific ways of deciding which orientation to make your base. Okay, so all we need to do is do top minus bottom. And if it's a vertical base, we know it's easier. We can just rely on the equations here. No need to adjust it. The top is the square root of x. And the bottom is the y equals x squared. Okay, so now we got to build the formula, the area formula for squares. So do you guys remember what the formula there is in terms of base? Yeah, just base squared. Okay, we insert that base, get the area. And now we just take this and insert it into our volume formula. Remember, your volume formula does not have pi in front. Okay, we're not rotating. There's not circles involved here. Okay, but we do need to find our bounds. Our bounds is going to be our x value from 0 to 1. 1 is the intersection between root x and x squared. And then take the area, whatever it is, and put integral and integral notations around it. Okay, so now it's just a matter of entering into your calculator. Your cross-section problems will feel very similar, assuming you can get to the base, either top minus bottom or right minus left, because really after that, you should figure out your formula, but your formula will be very similar to each other, regardless of the shape. It's always going to be base squared. You should have to figure out what the coefficient in front of it is, right? If it's an isosceles right triangle with leg on a base, it's going to be a 1/2 in front. If it's a right triangle with hypotenuse on the base, it'll be 1/4 in front. Equilateral triangles root 3/4. Semicircle is pi over 8. But they all include base squared for the most part, except for rectangles. Now, having said that, on the AP exam, squares are the ones that show up the most often. Okay, so that's good because that's the easiest one. We typically don't see these as much, but I mean, it's fair game. It's just this is the pattern. Most of the time, it's squares. Okay, try 15. 15 will feel like a virtual copy from 14, but just see if you can go through the same steps there. Top minus bottom, sine x squared minus 0 would just be sine x squared. Again, the shape that we're building is our squares. So base squared, and then just insert into your formula. Okay, any questions there, 15? All right, let's look at 16. 16, it says you have two curves here. Y equals 4 over x, y equals 5 minus x. And there's this axis of revolution is y-axis. Find the volume of the resulting object, okay? Now, anytime you have a 4 over x, 1 over x, or 2 over x, they're all going to kind of have this shape, this rational function shape, okay? But now we're only going to be looking at the first quadrant because the 5 minus x is only going to intersect that 4 over x there. So let's build our graph here. 5 minus x is going to be a graph that has a negative slope with a y-intercept at 5. So maybe something like this. axis of revolution, y-axis. Okay, let's look at what we're dealing with here. Is this going to be this method or washer method? Washer, right? There's no flat surface, horizontal or vertical flat surface on this shaded region. There's no chance that this could be this method anywhere, right? So, and we're never going to be rotating around a diagonal line. It's always around the vertical or horizontal line. So, okay, we know it's going to be washer method. Okay, is this going to be a top minus bottom or a right minus left? How is our radius going to look? Right minus left, right? Because we always have to extend from the axis of revolution. And in this case, we have to extend out to our shaded region. So from the dotted line, I'm going to extend out to my boundary twice. Once to reach the furthest boundary, and the other time to reach the closer boundary. And then I'm dealing with big R and little r. Okay. As soon as you see a horizontal radius, though, what do we have to be careful about? Yeah, the equation is not set up for right minus left. Most of your equation given is going to be set up for top minus bottom, but not right minus left. So we can't just insert them the way we see it. We got to rewrite them. Okay. So I'm going to rewrite the equation here. If I cross multiply here, xy equals 4, x equals 4 over y. Okay, so now it's in this more suitable form. Sorry. I also need to rearrange my linear equation, y equals 5 minus x. If I solve for x, all right, so these are my adjusted equation that I can use for my right minus left. Okay, big R. Right minus left, right endpoint is sitting at the 5 minus y, left endpoint is sitting at the 0. Okay, little radius, right minus left, right endpoint is sitting at the 4 over y, left endpoint is sitting at the 0. Right, the only thing that's left is figuring out the boundaries, right? So to find the boundaries, we know we still got to stick in terms of y here. So you look for intersections on your calculator, but maybe it's easier just to go ahead and set the two equations equal to each other. Okay, so I'll take my two equations here. Set them equal to each other and see if I can find my two intersecting points, which will act as my boundaries. Okay, cross multiply. Distribute the 5 minus or the y through. Okay, bring everything over to one side. Factor. And solve for y. Okay, so I have my boundaries. Lowest y value is 1, highest y value is 4, and now I'm ready for washer method. Okay, big pi first. Integral from 1 to 4. Big radius squared minus little radius squared dy. Make sure that you're squaring your radius separately. Your exponent should show up twice. You don't want to just do big R minus little r and just parentheses everything and just do the exponent once. You got to separate your exponent as two separate regions. Okay, 5 minus y first, and then 4 over y comes second. It's only asking you to set up, so this is a good potential problem for a non-calculator section where we can do everything without a calculator. And this is going to be answer choice C. Okay, number 17. What's the volume of the solid generated by the graph of x equals square root of y minus 2? And the lines x equals 0, x equals 5, revolved around the y-axis. Maybe you have don't know exactly what this graph looks like to even know what to sketch, but if it helps, maybe get it in terms of y first, and then maybe it becomes more visually easier to recognize. So if I square both sides here, I can solve for y. If I can solve for y, it becomes more familiar here. So if I solve for y, I get y equals x squared plus 2. Okay, we know what that looks like. That's just a parabola with a y-intercept of 2. And the square root just tells you that only the positive region is going to show up. Okay, so here's my graph. Okay, 0 and 5. So it's going to be like a kind of a quarter circle. Axis of revolution is y-axis. Okay, let's look at how this is set up here. Can we recognize this as disk or washer method? Disk, yeah. No gap up against a flat surface. Okay. Horizontal or vertical radius? Always perpendicular, right? So if I have a vertical axis, my radius has to be horizontal. So do we need to make any adjustment because this is a horizontal radius? Yeah, normally we would, but the equation is already given to us in the proper form, so we can just insert that, use that. This is already set up for us. So just have to find one big radius, big R. And then volume formula. Volume formula, all we require is big radius. No need for the small radius. Our bounds is easy to spot. There's no need to enter the calculator. Can you tell what the bounds are here? Yeah, in terms of y. So if you can sketch the graph out, you can tell lowest y value is 2, highest y value is 5. Big radius squared, dy. Answer choice E. Okay, your homework is, we did all of page 12, but I'll be checking pages 9 through 12 on Monday. I'll send out a reminder on Sunday.